So this is a problem guide going over how to do a Brayton cycle analysis with regen in it. In this problem, we're trying to determine the minimum flow rate of air needed for 110 megawatt net power output of a regenerative gas turbine. No constant variable heats, so we have to account for variable. We have a T1 of 300 degrees Kelvin, T6 of 1200 degrees Kelvin, and an overall compression ratio of 9. So, like after from 1 to 4. So it's always a good idea to sketch out a graph of these things, TS graph, so you can see where we're at. You can see we got Q out, Q in, label the temperatures, and the first thing we're going to want to do is find the work in. So to find the work in, we need to find the differences in enthalpy. But before we do that, we got to find the compression ratios, because we have the overall compression ratio is 9. And the overall compression ratio is equal to each individual compression ratio times each other. And we know that they're the same, so they both have to be 3. Now that we have the compression ratio, we can start trying to find the enthalpy here. So first we go to T1. We can see that the enthalpy there was real quick, but 300.19 kilojoules per kilogram. We also get a relative pressure of 1.36. And so we know that because of the compression ratio that the pressure at 2 is going to be 3 times the relative pressure at state 1. So that gives us a relative pressure of 4.158. And from there we can look up H2. We get 411.12 kilojoules per kilogram. So now we can calculate the work in. This is equal to H2 minus H1 plus H4 minus H2. But we can simplify this to 2 times H2 minus H1. They're both going to have the same amount of work. So we plug in our numbers, and we get 2 times 411 minus 300.19, all in kilojoules per kilogram, which gives us total work in of 222.13 kilojoules per kilogram. So in this next part, we need to calculate the work out. So the work done by both the turbines. We know we're starting with T6 of 1200 degrees Kelvin. From this, we can get our enthalpy as well as our relative pressure. So we go back to the ideal gas table. We get enthalpy equals 1,277 kilojoules per kilogram. Relative pressure equals 238. So opposite of our compressors, obviously our turbines are expanding. So it will be a decrease in pressure, 1/3. So 238 over 3, we get 79.33. And now we can go back, look up enthalpy. So it is 946.35 kilojoules per kilogram. And now we can find the work out. Same as we did it last time. We'll do 2 times H7 minus H6. And we just have a negative there so that we get a positive answer for the work out. So we have 946.35 negative 946.35 plus 1,277. So we get a net work out of 662 222.87 kilojoules per kilogram. All right, so we're finally almost there to calculate the mass flow rate. First, we need to calculate the net work, which is pretty easy. Work out minus work in. So that's why we had to get those. We get 662.87 minus 222.13, and that's all in kilojoules per kilogram. So once we do that, we get 440.73, and that's the work net output. So the work rate is equal to the mass flow rate times the work per kilogram. So we have 110,000 watts per second equals the mass flow rate times 440.73 kilojoules per kilogram, our work rate. So then if we rearrange that, we get the mass flow rate is equal to 110,000 watts over 440.73, and finally you get a mass flow rate of 249.586.